Hey friends, welcome to Chemistry Lover, and in this video I'll be talking about the photochemistry. So previously many of you have requested me to do video on for photochemistry, but for some reason I couldn't make that videos. But now you can see this is my fate that I'm enrolled in some lab where I have to do work on photochemistry, and basically the main work of our lab is the light triggered organic reactions and the measurement of the fluorescence property of the synthesized organic compounds. So that's why I have to read photochemistry in the advanced level, and I am also revising the basic topics of the photochemistry. So I thought I can make videos on photochemistry during this time, because that will be helpful for you also and for me also. So I am reading these things basically from a book by Lakovich. If you are interested in photochemistry, you can read that book. So now let's start today's topic. So if we talk about photochemistry, if we hear the word photochemistry, the first thing that comes in our mind is the phenomenon of luminescence, that is the fluorescence and the phosphorescence. Now what is luminescence? So before discussing about that, I want to tell you that fluorescence is a very important technique, and for the past 20 years it becomes a very highly used technique, the fluorescence spectroscopy, for the study of the different properties of the biologically important elements and other things. So day by day its importance is increasing, and that's why it is a very good topic. So let us come to our topic, that what is luminescence. So luminescence is basically whenever some molecule come back from a excited electronic state to a ground state, then some amount of energy is released, and this energy released in the form of light. So this emission of the light, this phenomenon of emission of the light during the comeback of a element or a molecule from excited state to the ground state is called as luminescence. Now this luminescence has two types. One is fluorescence, another one is phosphorescence, and this is classified according to the duration time of the event and also the nature of the excited state. For example, let us talk about fluorescence. So let's say you have an excited state of the molecule here and the ground state here. Now basically I am talking about the electronic states, and let's say you have two electrons. At first you have two electrons in the ground state. Now at first you excite one of the electron on the excited state. So let's say this is now the configuration of your overall system, that is this is the excited state and this is the ground state. But you can see the two electrons has the same spin. Two electrons has the opposite spin, that is they are spin paired. Now if this excited state electron has to come back to the ground state, it can come back, and for this it doesn't have to alter its spin, that is this process does not involve the change in spin. And whenever you don't have to change your spin in a transition process, that transition is spin allowed. So this particular phenomenon, this particular transition is spin allowed, and that's why it is a very fast process. The rate of this process is 10 to the power 8 second inverse. So you can see how fast the process is, and this is called the fluorescence. This transition is called fluorescence. Whereas let's say you have an excited state here and the ground state here, where your two electrons has the same spin, that is they are not spin paired, and when the excitation from higher excited state to ground state has to occur, this spin this electron has to alter its spin. You can see it has a up spin, but when it has to do the transition, it has to go to the down spin. So that means in this process it involves a change in spin state, and any transition which involves change in spin state, that is spin forbidden. So this transition is spin forbidden, that's why rate of this process is very slow. It generally remains 10 to the power 3 to 10 to the power 0 second inverse. Okay, and this phenomenon is called phosphorescence, and this is seen in the glow in dark toys. You have seen that that toys which glow in the dark, so they at first they have we have to shine them with light, and when we take them in dark they emit some light. So this is basically the phenomenon of phosphorescence. The excited phosphors come back to the ground state, and during that time the light it emitted from your toys. So this is an example of phosphorescence. So this phenomenon of fluorescence is first observed accidentally by William Herschel when he mixed the quinine sulfate. So before that, I want to tell you that some organic compounds, they are called fluorophores because they shows the event of fluorescence. And this is quinine. This is quinine. This is a very well known example of fluorophore, and it is used tremendously in many experiment of fluorescence. Other fluorescence are anthracene, pyrene, that molecules, and most of the polyaromatic organic molecules, they act as fluorophores. So let us come to our point that William Herschel, when he mixed the sulfate of quinine with tartaric acid and dissolved it with minimum amount of water and put it in a test tube, then he hold the test tube in sunlight, and although the solution was colorless, but after putting it on the sunlight, he observed that there is a very beautiful blue color which appears on the top surface of the test tube, that is just at the surface of the solution. So at that time there was no such good explanation for this event, but later another famous scientist, Stokes, he did the experiment on the same thing, and later it is find out that it is the event of fluorescence. Now another historical perspective is that the first fluorospectrometer was developed during World War I, and you know that drug of malaria contained the quinine. So they has to examine the properties of this malaria drug, and for that they want to measure the fluorescence properties of the drug which has the quinine moiety. So that's why they developed the first fluorescence spectrometer, and you can see this is another gift from the World War I. So now to explain or to illustrate all this phenomenon of light absorption and emission, the most effective tool or the most effective method is to explain it with the Jablonski diagram. And Jablonski is said to be the father of the fluorescence spectroscopy. So you can see this is basically a Jablonski diagram. So we will show the different events which occur during the light emission and absorption process during a fluorescence or the phosphorescence event. So these are schematic representation of the different energy states of a molecule. This is a singlet electronic state, and these are the other excited state. For example, S1, this is excited singlet electron state first. This is the second excited electron state, which is also singlet, and this is a triplet excited electronic state. There may be other singlet state, but for our illustration, these four energy levels are enough. And you can see these small energy levels within this every singlet or triplet state, they are actually the vibrational energy levels, and each of the electronic state accompany with them several vibrational levels, and we just have shown 3 of them in each cases. Now let's say you have a substance A and you excite it with some radiation which has frequency, let's say a nu A. So it will be excited to A star, which is a excited electronic state of A. So that means you are promoting your molecule from this singlet ground state to some excited state. Now this promotion may occur from this S0 to S1, but at the same time it can happen from S0 to S2 also. Okay, so this is H nu A and this is H nu A dash. This is the process called absorption. This is the absorption event. Now after going to the excited electronic state, the first thing which will occur is that the molecule will come back to the the first excited state among this all the energy state, and also the ground vibrational level of the first excited state. That means if the molecule is here first, it will come back to this first vibration level. If it is 0 vibration level, then it is 1, 2 and 3. So these are the vibrational level. So first what will happen, the molecule will come to the ground vibrational level of a particular excited singlet state, and for this singlet state also it will come back to this state. Okay, so this is 0, this is 1, this is 2, 0, 1 to represent the vibrational state. Now you can see these singlet excited state and this singlet excited state, they overlap with one another, and that means this molecule can cross over to this excited state and it can again come back to here. So these processes are non-radiation process, that is no radiation is emitted during this process, and these are called internal crossover, internal crossover or internal conversion. So it is represented as IC. So this process is called IC. Now when all the molecules come back to this ground vibrational level of S1 state, then it will revert back to the, either it can go to the some excited vibrational level of ground electronic state, or it can go to the ground vibration level of the ground state. Okay, so this process is called fluorescence and it is represented by H nu F. Now you can see this is a radiation process, that is in this process radiation is emitted from the molecule, and that's why it is a radiation process and it is called fluorescence. Now the time requirement for this internal conversion is generally 10 to the power 12 second, whereas this fluorescence, the lifetime for this fluorescence event is 10 to the power minus 8 second. We already told that the rate of this process is 10 to the power 8, so that means the time requirement should be 10 to the power 8. Now you can see that means sorry, this should be 10 to the power minus 2. So that means this internal conversion, this is a very much faster process than the fluorescence process. That means all the excited before the fluorescence to occur, all the electrons in the excited states will first come back to the ground vibrational level of the first excited state. So fluorescence cannot happen from the S2 level. It will always occur from S1 level and also from the ground vibrational level of the S1 electronic state. Okay, now another thing can happen is that from this S1 state electron may go to this T1 state also, but in this case you can see, although in the previous case from S2 to S1, that is a spin allowed process because both are singlet, but in this case from singlet to triplet the process is occurring, and that's why it is a spin forbidden process. So this process is very slower and it is called inter-system crossing, ICS. This is called inter-system crossing because ISC, inter-system crossing, because this is occurring from a singlet system to a triplet system. So internal crossover is occurring, but the systems are different. So that's why it is called inter-system crossing. Now again, the molecule will come back to the ground vibrational level of the first excited triplet state, and from there the phenomenon of phosphorescence occurs. So this is now called H nu P. So this is called phosphorescence when the excited molecule come back from the excited triplet state to the singlet ground state. So this is called phosphorescence, and you can see both of this phenomenon occurs from some triplet to singlet or singlet to triplet. That means this is a spin forbidden process, and that's why it is a slow process, and its rate is generally 10 to the power 3 to 10 to the power 0. So phosphorescence is a slower process than a fluorescence process. Now in the fluorescence spectroscopy, if we plot the graph, we generally plot the intensity versus wavelength or intensity versus wave number. So this axis, this y-axis represents the intensity, and this x-axis represents the the wavelength or the wave number. Now basically we put the absorption and the emission spectra, and fluorescence spectra is basically emission spectra. But let us now talk about the Stokes Shift. So what is Stokes Shift? So you can see, if you consider the energy difference between the S0 or S1 or S0 and S2, you can see the wavelength which is absorbed during the excitation of the molecule, it is always greater than the wavelength which is emitted during the de-excitation of the molecule. Why? Because you can see when the excitation occurs, either the molecule go from the ground vibrational level to the some high energy electronic states and also its higher vibrational level. So you can see from ground vibration level, this is V equal to 0. From V equal to 0, so from V equal to 0 of S0, it is exciting to V equal to 4 of S2 or V equal to 3 of S1, right? But during the emission, it always occurs from the ground vibrational level of the first excited state. So this energy gap, if it is delta E, then the energy gap when the excitation occurs, for example, let's say delta E dashed or delta E double dashed. So this delta E double dashed or delta E so delta E dashed or delta E double dashed, it is always greater than your delta E. That means the energy difference which has to travel during the excitation and the energy difference which has to travel during the de-excitation, they are different, and energy requirement is higher for the excitation than that of the de-excitation. So that means if we plot this phenomenon in this intensity versus wavelength curve, we will see two curves like this. So you have to identify these two curves. So low energy means wavelength will be higher. So your de-excitation occurs at low wavelength, de-excitation occurs at low energy, that means it will occur at high wavelength. So in this particular diagram, this is your fluorescence diagram, and this is your absorption. Okay, so your fluorescence peak, this is the fluorescence peak. Your fluorescence peak for a particular molecule will always be at greater lambda value than the absorption peak. I again repeat that fluorescence peak will always be at the right hand side, that is at greater lambda than your absorption peak. Why? Because fluorescence occurs at lower energy difference than the absorption. Okay, so this is one event, and this shift of wavelength is called the Stokes shift. We will later discuss in detail about the Stokes shift. So, and another interesting thing is that let's say you have some molecule, for example anthracene. Anthracene is also a fluorophore, and it shows the fluorescence phenomenon. And if you plot the absorption and fluorescence pattern of anthracene, you will see a diagram like this. Sorry. You will see a diagram like this. So you can see there is a perfect mirror image relationship. So this is basically the absorption process, and this is the fluorescence process. So you can see the absorption spectra is just looks like the mirror image of the fluorescence spectra. Now why this is so? So this is a very interesting phenomenon. Now for that we have to draw the energy level diagrams once again. So let's say this is the ground state S0 of your anthracene, and this is some electronically excited state S1 of your anthracene. Now at first the excitation may occur from this 0, so this is V equal to 0, this is V equal to 1, this is 2, this is 3, for this also this is 1, 2, 3 and 4. Sorry, 0, 1, 2, 3. Right. Now from V0 the excitation can occur to V3 or to V2 or to V1 or to V0. Okay, but when the de-excitation or the phenomenon of fluorescence occur, it will always occur from the 0 level of S1. So it can occur from 0 to 0 or 0 to 1 or 0 to 2 or 0 to 3. That means in every case the phenomenon occurs from 0 to 1, 0 to 2, 0 to 3 and 0 to 0. This is the phenomenon for your absorption process, and the same phenomenon occurs from for the fluorescence process, that is 0 to 0, 0 to 1, 0 to 2 and 0 to 3. Only the difference is that in this case this 0 is the 0th vibrational level of your ground state, but in this case the 0 is the 0th vibrational level of the first excited electronic state. Now we have to discuss about another principle, that is the Frank-Condon principle, which says that during the electronic transition there is no change in the nuclear position of the molecule, or there is no change in the geometry of the nucleus. That means these processes, this fluorescence process, we already told that it is a very fast process. It occurs in 10 to the power 8 second inverse rate. So it is a very fast process, and during this process there is no chance for the alternation or the change in the geometry of the nucleus. So that means the geometry is fixed, and that's why the spacing between vibrational level for the ground state and the fast excited state or any other excited state will also be similar. So due to the Frank-Condon principle, which says that the electronic during electronic transition no change in nuclear coordinate occurs, so its effect will be that the energy difference between any two vibrational levels in the ground state will be same with that of any excited state. So that means that this energy will be different. That means this 0 to 0 and this 0 to 0, their energy will be different. For 0 to 1 or this 0 to 1, their energy should be different. But the transition probability, the whether the transition is allowed or not, or how fast the transition will be, that is which is manifested in the intensity of the current, that will be same in every case, because you can see in this case also it is 0 to 0, in this case also it is 0 to 0. So the transition probability is same in all cases because of the Frank-Condon principle, and that's why the peak, the size of the peak or the nature of the peak for 0 to 0 here and 0 to 0 here will be same, and that is manifested in this spectra. That is the absorption spectra just look like the mirror image of the fluorescence spectra. So now this is not true for every cases, okay, because you can see if the electronic transition occurs from some S2 state, then it will not match with the absorption pattern, right? But this is a very rare case. In most of the cases, 99% of the cases, the fluorescence spectra and the absorption spectra just look like similar, and they looks like a mirror image of one another. But in some cases the difference are there, and in the next video I will discuss about that differences, and also another important topic, that is the time duration or the average time for the fluorescence spectroscopy. And I will in this series I will discuss all the photochemistry event, the photochemical reactions of the organic compounds also. So for that you have to subscribe my channel, and if you like this videos then give a thumbs up and share this video with your friends. Thank you for watching.